Empty space is never truly empty. It crackles with a ghostly energy, a constant flicker of creation and destruction happening everywhere all the time. These are quantum fluctuations, the universe's most fundamental and bizarre behavior. They are not just microscopic blips, but the very seeds from which all of reality grows. By staying until the end, you will journey through 30 mind-bending theories that reveal how these tiny tremors dictate everything, from the birth of our cosmos in the Big Bang to its ultimate fate in the far future. We will explore how a random flicker could spawn an entire universe from nothing, and whether the solid world around you is just a hologram projected from its edge. What single idea about reality would you be willing to question? The very first theory strikes at the heart of our understanding, revealing a terrifying miscalculation. It is called the vacuum catastrophe, and it begins with a simple, profound question. What is the energy of nothing? According to quantum field theory, the vacuum of space is not a serene, empty void. It is a seething, turbulent ocean of quantum fluctuations, where virtual particles pop in and out of existence constantly. Every cubic centimeter of what we call empty space should be packed with a staggering, almost infinite amount of this vacuum energy. Physicists can calculate this predicted energy density, and the number they get is astronomically, impossibly large. It suggests a force so powerful that it would have caused the universe to expand with such violent fury that not a single atom, not a single star, not a single galaxy could ever have formed. The cosmos would have been torn apart in an instant. Yet here we are. Our telescopes show a universe that is expanding, yes, but at a much, much gentler pace. The actual observed energy of the vacuum, often called dark energy, is 120 orders of magnitude smaller than the prediction. That is a 1 followed by 120 zeros. It is the worst mismatch between theory and observation in the entire history of science. This is not a small error. It is a complete and utter failure of our most fundamental theories to explain the very fabric of space itself. The vacuum catastrophe stands as a monumental warning, a direct signal from the quantum foam that we are missing something essential, something that tames the furious energy of nothing into the quiet hum that allows our reality to exist. This staggering error forces us to reconsider everything, including the biggest question of all. Where did everything come from? The second theory offers a breathtaking answer. Our entire universe, with all its galaxies, stars, and planets, may be nothing more than a single, monumental quantum fluctuation. This is the idea of a universe from nothing. Think back to that seething quantum foam, where particle-antiparticle pairs blink into existence by borrowing energy from the vacuum. Quantum mechanics allows for these temporary violations of the classical rules, so long as they happen quickly enough. Now, expand that idea to its ultimate extreme. What if, instead of a single particle pair, the entire fabric of spacetime itself fluctuated into being? Physicists like Lawrence Krauss have explored this radical possibility. They describe a state of true nothingness, not an empty void within space, but the absence of space and time themselves. In such a state, the laws of quantum uncertainty still apply. There is always a probability, however small, for something to appear. In this framework, the universe did not explode from a singular point of infinite density. It quantum tunneled into existence from a state of no space, no time, and no matter. It was a random, spontaneous event, the ultimate free lunch. The total energy of our universe might actually be zero when you account for a cosmic ledger. The positive energy bound up in all the stars and galaxies is perfectly balanced by the negative gravitational energy of their attraction. So, from a quantum fluctuation in a primordial nothing, a universe with zero net energy simply appeared. One moment, there was nothing. The next, there was an embryonic cosmos, inflating and cooling into the vast reality we observe today. This means our home, in all its complexity and beauty, could be the result of the same fundamental randomness that creates a virtual particle in your living room. We are not the center of a grand design, but perhaps the most spectacular accident in an eternal, fluctuating void. If our cosmos is a single quantum blip, what lies beyond its boundaries? The third theory suggests we are not alone, but merely one bubble in an infinite, frothing cosmic sea. This is the concept of eternal inflation and the multiverse. To understand it, we must revisit the earliest moments after the Big Bang, during a period called cosmic inflation. For a fleeting fraction of a second, the infant universe expanded faster than the speed of light, stretching from a subatomic speck to a volume larger than our entire observable cosmos. This explosive growth was driven by a hypothetical energy field called the inflaton field. Now, here is where quantum fluctuations become the architects of reality. Just like the vacuum of space, this inflaton field was not perfectly smooth. It was roiling with quantum jitters, tiny random variations in its energy. In most regions, the inflaton field eventually lost its energy, settling down and slowing its expansion. That transition is what created the hot, dense soup of particles that became our familiar universe. But according to eternal inflation, in some regions, a random quantum fluctuation kept the inflaton field energized. In those pockets, inflation never stopped. It kept going, exponentially expanding space at an unbelievable rate. And within that eternally inflating background, quantum fluctuations could cause new pockets to drop out of inflation, each one creating its own separate, isolated universe, like a bubble forming in a rapidly rising loaf of bread. Each of these bubble universes would cool down with its own random set of physical constants, born from the particular quantum dice roll that created it. In one bubble, gravity might be vastly stronger, instantly crushing any structure. In another, the nuclear forces might be too weak to ever form atoms. Our universe, with its just right balance allowing for stars, planets, and life, is not special by design. It is simply a bubble where the quantum lottery produced a winning ticket. This means the multiverse could be an unending fractal landscape, a chaotic foam of universes bubbling into existence forever, each with its own laws, its own history, and perhaps its own version of you, living a life dictated by a different set of quantum rules. But how could such randomness ever produce the grand, organized structures we see today? The fourth theory provides the astonishing answer. Those same quantum fluctuations that birthed the universe also wrote its entire blueprint. They are the original seeds for every galaxy, every star, and every planet in existence. This story begins in the first fleeting moments of the cosmos, during that same inflationary period. Remember the inflaton field, that energy driving the universe's explosive growth. It was not a perfectly smooth, placid lake. It was choppy with quantum ripples, tiny variations in energy from point to point. These were the most fundamental vibrations of reality itself, random and unpredictable. As inflation stretched the fabric of spacetime at an unimaginable rate, it did something miraculous to these tiny quantum ripples. It stretched them too. A fluctuation that was once smaller than a subatomic particle was blown up to a size larger than our entire observable universe. Inflation took the microscopic quantum noise and imprinted it onto the cosmos at a colossal scale. When inflation ended, these stretched out fluctuations became slight differences in the density of matter and energy across the newborn universe. Where the quantum field had a tiny peak, there was a tiny bit more mass. Where it had a tiny valley, there was a tiny bit less. These minute differences, these cosmic seeds, were frozen into the fabric of reality. Then, gravity took over. Over hundreds of millions of years, gravity began to pull matter toward those denser regions. The slightly denser spots pulled in more and more gas and dark matter, growing heavier and more attractive. The slightly emptier regions were drained. This gravitational tug of war, acting on those initial seeds, is what sculpted the cosmic web we see today. The great clusters of galaxies, the long filaments of dark matter, the vast empty voids, all trace their lineage directly back to those random quantum jitters in the first instant of time. We have a direct snapshot of this moment, a fossilized imprint of those quantum seeds. It is the cosmic microwave background, the afterglow of the Big Bang. This faint microwave light that fills the entire sky is not perfectly uniform. When we map it with incredible precision, we see a modeled pattern of hot and cold spots, temperature variations of just a few millionths of a degree. Those spots are not random noise. They are the exact pattern of those primordial density fluctuations stretched across the sky. That map is the universe's baby picture, and the freckles on its face are quantum fluctuations, magnified to a cosmic scale. So every structure you see in the night sky, every spiral galaxy, every burning star, every orbiting planet, exists because of a random quantum dice roll in the first fraction of a second of everything. The universe did not start with a plan. It started with a whisper, a quantum whisper that gravity amplified into a symphony of stars. That cosmic baby picture, imprinted with quantum whispers, suggests a reality built from information. But what if that information is not stored within the space we experience? Theory 5 shatters our perception of dimensions entirely. It proposes that our three-dimensional universe, with all its galaxies, black holes, and quantum fluctuations, is not the fundamental reality. It is a hologram. Every event, every particle, every flicker of energy we perceive in the vast volume of space might be a projection from a flat, two-dimensional surface at the very edge of everything we can see. This is the holographic principle, and it turns our understanding of reality inside out. The idea emerged from the study of black holes, the ultimate cosmic paradoxes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, a measure of its hidden information or disorder, is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon, the point of no return. This was bizarre. It suggested that all the information about everything that ever fell into a black hole is not lost inside its mysterious singularity, but is somehow smeared and encoded on its two-dimensional boundary. Later, string theorists like Leonard Susskind and Gerard T. Hooft took this radical notion and applied it to the entire cosmos. They proposed that our universe might operate on the same principle. The three spatial dimensions we move through could be an illusion, a grand cosmic projection. The true, fundamental description of reality exists on a distant, two-dimensional surface that encloses us. Think of it like a credit card hologram. The flat, shiny sticker contains all the information needed to generate a three-dimensional image that seems to float in space. In the cosmic version, the flat surface is the boundary of the observable universe. and the three-dimensional image is everything within it, including you watching this. This has a profound implication for quantum fluctuations. If our reality is holographic, then those seething virtual particles and energy flickers are not fundamental features of empty space. They are emergent phenomena. They are the pixelated noise, the granular texture, that arises when a vast amount of information on a two-dimensional surface is translated into a three-dimensional projection. The quantum fuzziness we detect might be a side effect of this cosmic encoding process, like static on a television screen emerging from the broadcast signal. The holographic principle suggests that at the most basic level, the universe is not made of things but of bits. It is a cosmic computation, and the drama of quantum fluctuations is the visual output of a deeper informational process happening on a flat screen at the edge of everything. A holographic universe built from information leads to an even more unsettling possibility. If reality is a projection or a computation, could it be an artificial one? This brings us to Theory 6, the simulation hypothesis, a modern philosophical idea that our entire cosmos, and everyone in it, might be running inside a vast, sophisticated computer. Proponents like philosopher Nick Bostrom argue that if any advanced civilization ever reaches the capability to create realistic simulations of conscious beings, the number of simulated universes would vastly outnumber the one base reality. Statistically, we are more likely to be inside one of those simulations than in the original world. But how could we ever test such a fantastical idea? Some scientists suggest we should look for glitches in the matrix, and quantum fluctuations might be the very evidence we seek. In this view, the seething quantum foam is not a fundamental feature of nature. It is the background noise, the computational rounding errors, of the simulation's rendering engine. Think of a modern video game. To create a vast, open world, the game engine does not calculate every single blade of grass in perfect detail all the time. It uses tricks. It renders only what the player can see, and it approximates distant objects with lower resolution textures. The world appears continuous and real, but under the hood, it is made of discrete pixels and limited processing power. Now, imagine a simulation of an entire universe. The creators would need to be unimaginably advanced, but they would still face fundamental limits. They could not simulate every single subatomic particle with infinite precision in real time. At some point, to conserve computational resources, the simulation would have to approximate. It would round off numbers. It would quantize energy and space into the smallest possible packets. This is exactly what quantum mechanics tells us about our own reality. Energy does not flow in a smooth, continuous river. It comes in tiny, indivisible chunks called quanta. Space and time themselves might be pixelated at the tiniest scale, a concept known as the Planck length. These discrete, grainy properties of our universe are exactly what you would expect from a simulation running on finite hardware. The constant buzz of virtual particles popping in and out of existence could be the visual static produced by the simulation's processor as it calculates the vacuum state. The famous double-slit experiment, where a single particle seems to pass through two slits at once until you look at it, could be interpreted as a rendering optimization. The simulation does not bother to calculate a definite path for the particle until an observer, a conscious entity within the program, forces it to resolve the calculation and produce a concrete result. It is a cosmic version of lag. Of course, this remains a fringe and highly speculative idea, more philosophy than proven physics, yet it forces a profound question. If we ever discovered undeniable proof that quantum randomness was actually the hum of a cosmic computer, would that make our lives, our loves, and our struggles any less real? Or would it simply reveal the astonishing architecture of a reality far stranger than we ever dreamed? But if reality is a projection or a simulation, who is the observer? Theory 7 takes this question to its ultimate, mind-bending conclusion. It suggests that observers are not just passive witnesses to the universe. They are the very mechanism that brings it into being. This is the participatory anthropic principle, a radical idea championed by the legendary physicist John Archibald Wheeler. To understand it, we must revisit the most famous oddity in quantum mechanics, the double-slit experiment. When you send a single particle, like an electron, toward a barrier with two slits, it does not go through one slit or the other. It behaves as if it goes through both simultaneously, creating an interference pattern on a detector screen. This is the particle existing in a superposition, a ghostly blend of all possible paths. However, if you place a measuring device to watch which slit the electron goes through, the magic vanishes. The particle instantly picks one definite path, and the interference pattern disappears. The act of observation, of measurement, forces the fuzzy cloud of possibilities to collapse into one concrete reality. Wheeler took this bizarre quantum rule and applied it to the cosmos. He proposed a thought experiment called the delayed choice experiment. Imagine a single photon from a distant quasar, a star billions of light years away. On its journey to Earth, it can be gravitationally bent around an intervening galaxy, taking two possible paths that eventually recombine. Using a telescope, we can choose to measure which path the photon took, forcing it to have had a definite history. Or we can choose to measure the interference between the paths, proving it took both routes. The staggering implication is this: our choice of measurement today, right now, determines what that photon did billions of years in the past. The present is reaching back and shaping history. Wheeler then scaled this up to the entire universe. He asked, if a quantum phenomenon is not observed, does it really happen? In the beginning, the universe was a quantum fluctuation, a superposition of countless possible states. For billions of years, it expanded and evolved in this fuzzy, undefined potential. There were no observers, no eyes to look. So what collapsed this cosmic wave function into the specific, tangible reality we inhabit? Wheeler's answer is a cosmic loop. The universe evolved in such a way that it eventually produced conscious observers. And those observers, by looking back at the universe's origins, through telescopes and particle detectors, performed the ultimate delayed choice experiment. Our observation of the cosmic microwave background, of the light from the first galaxies, of the very quantum fluctuations we have been discussing, is the act that retroactively solidified the universe's history. We are not just living in the universe. The universe exists in order to produce us, and we, in turn, bring it into concrete existence by observing it. The quantum fluctuations were not just seeds. They were a set of questions, and our consciousness is the answer that gives them meaning. In this view, the Big Bang did not truly finish until the first conscious being looked up at the stars and wondered where they came from, completing a circuit of reality that spans all of time. That cosmic observer loop requires a tangible force, a real pressure from the quantum void. And we have not only theorized it, we have measured it. This brings us to Theory 8, the reality of zero-point energy and the Casimir effect. Forget the idea of absolute emptiness. Even at absolute zero, the temperature where all classical motion ceases, the vacuum still hums with an irreducible energy. This is the zero-point field, the lowest possible energy state of a quantum system. It is not empty. It is a simmering broth of fleeting electromagnetic waves and virtual particles, a consequence of the fundamental uncertainty principle that forbids perfect stillness. This energy is not just a mathematical abstraction. It exerts a physical force, and we can prove it with a simple yet profound experiment. Picture two perfectly smooth, uncharged metal plates placed incredibly close together in a perfect vacuum, parallel to each other. In the classical world, with nothing between them and no charge, nothing should happen. They should just sit there. But in our quantum reality, something remarkable occurs. The space between the plates is restricted. Only certain wavelengths of the vacuum's quantum fluctuations can fit between them, like specific musical notes resonating in a pipe. Outside the plates, in the wider vacuum, fluctuations of all wavelengths can exist. This creates a difference in pressure. The relentless push of virtual particles from the outside is slightly greater than the push from the restricted fluctuations between the plates. The result, the plates are pushed together by the sheer pressure of nothingness. This is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948, and experimentally confirmed with increasing precision in the decades since. It is direct, tactile proof that the quantum fluctuations of the vacuum are real. They are not just theoretical ghosts. They have measurable consequences, a literal force you could feel if you could hold those plates. This zero-point energy is unimaginably dense. Calculations suggest that a single cubic centimeter of pure vacuum contains more energy than all the matter in the entire observable universe. Yet, we cannot tap into it because it is the baseline, the floor state of reality. Every particle, every field, is already vibrating atop this eternal hum. The Casimir effect shows us that empty space is alive, a dynamic medium whose hidden activity shapes the very forces between objects. It is the silent, constant pressure of creation and annihilation, and it holds every atom in the universe just a fraction of a nanometer apart from collapse. The tangible pressure of the Casimir effect proves the quantum vacuum is real, but its true power remains locked away. This brings us to a theory that could solve the greatest mystery in modern cosmology. What if the relentless energy of these quantum fluctuations is not just a background hum, but the very engine tearing the cosmos apart? This is the bold proposition linking quantum vacuum energy to dark energy. For decades, astronomers have known the universe is not just expanding, but that this expansion is accelerating. Something is pushing galaxies apart with ever-increasing force, acting against the pull of gravity. We call this something dark energy, but its nature is utterly unknown. It constitutes about 68% of everything in the universe, yet we have no idea what it is. One of the most compelling candidates has always been right under our noses, or rather, woven into the fabric of empty space itself. It is the zero-point energy of the quantum vacuum. The idea is beautifully simple and profoundly troubling. That seething sea of virtual particles we just proved exists with the Casimir plates, carries an inherent energy density. If this vacuum energy is constant, unchanging as the universe expands, then it would act exactly like dark energy, producing a repulsive force that drives acceleration. It is a perfect theoretical match. One mystery, the quantum vacuum, could elegantly solve another, the fate of the cosmos. But here we collide headlong with the vacuum catastrophe, that 120 orders of magnitude problem. When physicists calculate the predicted energy density of the quantum vacuum using our best theories of quantum fields, the number is astronomically, catastrophically wrong. The theoretical vacuum energy is 10 to the power of 120 times larger than the observed value of dark energy. To put that in human terms, it is the difference between the energy in a single drop of water and the energy in all the oceans on every planet in a billion galaxies. It is not even close. This is the most embarrassing failure in physics. We have identified a suspect for dark energy that fits the profile perfectly, but the suspect is 10 trillion times more powerful than the crime scene evidence suggests. So, is the link broken? Not necessarily. This monstrous discrepancy is not seen as a dead end, but as the most important clue we have. It screams that our understanding of the quantum vacuum is fundamentally incomplete. Solving this problem would require a revolution, perhaps a new theory that marries quantum mechanics with gravity, a theory of quantum gravity. Maybe the vacuum energy is not constant, but evolves. Perhaps it is somehow cancelled out by another unknown field. Or maybe, in a twist of cosmic irony, the infinite positive and negative contributions from all possible virtual particles sum up to a very small, non-zero number, not a colossal one. Finding the right calculation, the one that tames infinity into the tiny number we observe, would be one of the greatest triumphs in human thought. It would mean we finally understand the true nature of nothing, and in doing so, unlock the secret of everything. The fate of the cosmos, whether it expands forever into cold darkness or meets some other end, hinges on the precise value of a number born from the ghostly flicker of particles that do not exist. The immense energy of the quantum vacuum could hold the key to cosmic fate, but it also guards a fundamental rule of reality. Stephen Hawking proposed a remarkable idea to protect the very fabric of time itself, a concept he called the chronology protection conjecture. Hawking was deeply troubled by a strange possibility allowed by Einstein's theory of general relativity. The equations suggest that under extreme conditions, like those around a rotating black hole or a cosmic string, space-time could twist so severely that it forms a closed time-like curve. This is a path through space-time that loops back on itself, allowing an object to return to its own past. In essence, it is the mathematical blueprint for a time machine. The existence of such a loop would shatter our understanding of cause and effect, opening the door to paradoxes like the famous grandfather paradox, where you could go back in time and prevent your own birth. Hawking found this deeply unsettling, believing the universe should not allow such logical absurdities. He argued that nature must have a law to prevent it. His proposed mechanism was not a cosmic police force, but the relentless, amplifying power of quantum fluctuations. Here is how it would work. Imagine a closed, time-like curve beginning to form. As particles, and especially light, travel around this loop, they would pass through the same region of spacetime again and again with each circuit. Now introduce the quantum vacuum. That sea of virtual particles is not silent. It is filled with fluctuations in all quantum fields, including the electromagnetic field, which we perceive as fleeting bursts of light. In normal space, these fluctuations are tiny and transient, but near a forming time loop, something catastrophic would happen. A single virtual photon, a particle of light flickering into existence from the vacuum, could enter the loop. It would travel back in time a tiny bit, then re-enter the present, merge with its own past self, and loop again. With each cycle, the photon's energy would build upon itself, amplifying over and over in a runaway feedback loop. The quantum fluctuation would not remain a tiny, ghostly event. It would grow exponentially, becoming an infinitely intense beam of radiation. This unimaginable surge of energy would warp spacetime so violently that it would destroy the closed time-like curve before it could ever be used. The time machine would literally tear itself apart from the inside out, fueled by the amplified buzz of the quantum vacuum. In Hawking's view, the universe is not just random at the quantum level. It is fiercely protective of chronological order. The same ghostly flickers that seeded galaxies act as a cosmic immune system, attacking any anomaly in spacetime that threatens to create a paradox. The quantum foam is not just the substrate of reality. It is its guardian, ensuring that time flows in one direction, that causes always precede effects, and that history remains a singular, unchangeable thread. We are not prevented from time travel by a lack of technology, but by the fundamental laws of quantum physics, which would unleash hell to stop us. The universe's guardianship of time reveals a startling truth about its very fabric. At the tiniest imaginable scale, reality dissolves into pure chaos. This is the theory of spacetime foam, a vision of the cosmos so alien it makes the quantum vacuum seem placid. We perceive space and time as a smooth, continuous stage, a blank canvas upon which events unfold. But if we could peer down to the Planck scale, a distance so small it is a decimal point followed by 34 zeros and a 1, that smoothness shatters. There, spacetime itself is not a fixed background. It is a seething, turbulent froth, a foam of quantum fluctuations. In this frenzied domain, the geometry of the universe is not defined by elegant curves or straight lines. It is a constantly churning mess of probabilistic bubbles, twists, and tunnels. The very concepts of here and there, before and after, lose their meaning. In the foam, microscopic wormholes blink into existence, connecting separate points in an instant, only to pinch shut and vanish a moment later. Tiny baby universes may bubble up as self-contained spacetime structures, inflating for a fleeting moment before collapsing back into the quantum soup from which they came. This is not happening in space. This is what space is made of at its most fundamental level. The foam is not within the universe at its root is the foam. This idea, first proposed by physicist John Wheeler, directly challenges our classical intuition about geometry and causality. In our everyday world, geometry is rigid. The shortest distance between 2 points is a straight line, and causes always precede their effects. In the spacetime foam, geometry is dynamic and probabilistic. A particle's journey from A to B is not a single path. It is a sum over all possible histories, including paths that dive through a fleeting wormhole and reappear instantly, or that loop around a temporary bubble universe. Causality, the unbreakable chain of cause and effect, becomes fuzzy. In that frenetic foam, could an effect briefly precede its cause on a microscopic scale? The foam suggests that the orderly flow of time we experience is not fundamental, but an emergent property. It is the statistical average of unimaginable chaos, like the smooth surface of a lake emerging from the frantic motion of countless water molecules. Our reality, with its clear distances and definite past, is what happens when you zoom out from the quantum frenzy. We are living on the calm, classical surface of a deep, frothing ocean, whose depths defy every rule we hold sacred. That fundamental chaos of spacetime foam finds its ultimate expression in the darkest corners of the cosmos. At the edge of a black hole, quantum fluctuations are forced to play a deadly game with the laws of physics, a conflict that threatens to unravel reality itself. This is the black hole information paradox, and it begins with a simple, profound rule of quantum mechanics. In our universe, information is never truly lost. If you burn a book, the ashes and smoke seem to erase its story. But in principle, if you could track every single particle and measure every quantum state with infinite precision, you could reverse the process and reconstruct the book perfectly. Information is preserved, scrambled, but never destroyed. This is a sacred principle. Now, throw a book into a black hole. According to Einstein's classical theory of general relativity, the book crosses the event horizon, the point of no return, and is lost forever. Its information is crushed into the singularity at the black hole's center, severed from our universe. For decades, this was seen as a strange but acceptable loss. Then, in the 1970s, Stephen Hawking made a revolutionary discovery. He realized that black holes are not completely black. They can glow and they can evaporate. This Hawking radiation is born directly from the quantum fluctuations at the event horizon. Remember the virtual particle pairs that constantly flicker in and out of the vacuum. Normally, they annihilate each other almost instantly, but right at the precipice of a black hole's gravity, something sinister can happen. One particle of the pair falls inward, crossing the horizon, while the other escapes into space. To an outside observer, the black hole has just emitted a particle. The energy for this emission comes from the black hole's own mass. Over astronomical timescales, this slow leak of Hawking radiation causes the black hole to shrink and eventually vanish entirely. Here lies the paradox. The radiation that escapes is purely thermal, like the heat from a stove. It is random noise, carrying no information about what fell into the black hole. When the black hole finally evaporates, all that remains is this featureless thermal radiation. The information about the book, the star, the planet that formed the black hole, is seemingly erased from existence. This violates the core tenet of quantum mechanics. We are left with a catastrophic choice. Either our understanding of quantum information is wrong, or our understanding of black holes and gravity is profoundly incomplete. This paradox festered for decades until it spawned an even more frightening idea, the firewall paradox. If information must escape a black hole, perhaps it does not leak out slowly with Hawking radiation. Maybe it is imprinted on the event horizon itself in a scrambled code. But for an astronaut falling into the black hole, the horizon should be uneventful, a smooth point of no return they cross without noticing, according to Einstein. However, if the horizon is a blazing wall of encoded information, the astronaut would be incinerated instantly by a firewall of unimaginable energy. This creates an impossible contradiction between the smooth spacetime of general relativity and the informational demands of quantum theory. Resolving this paradox may force us to rewrite the rules of quantum fluctuations themselves. Perhaps the fluctuations at the horizon are not simple particle pairs, but are deeply entangled in a complex web that preserves information in a way we cannot yet see. Or maybe the event horizon is not a sharp boundary, but a fuzzy, fluctuating region where our classical notions of space and time break down completely. The answer will not just tell us the fate of information in a black hole. It will reveal how the ghostly tremors of the quantum vacuum stitch together the fabric of space-time, gravity, and information into a single, coherent reality. The ultimate evaporation of a black hole leaves behind only random radiation, a thermal whisper with no memory of what fell in. This erasure of information seems to violate a sacred rule, but it also points to a deeper mystery about time itself. Why does time flow in one direction? Why do we remember the past but not the future? the answer may be written in the very first quantum fluctuations. Theory 13 proposes that the arrow of time, the irreversible flow from order to disorder, was not a given. It was a choice made by the universe in its first instant, dictated by the specific pattern of its quantum seeds. To understand this, we must grasp a concept called entropy. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This is why a dropped glass shatters and never reassembles itself, why ice melts in your drink, and why we grow older. It is the physical reason time has a direction. But this law presents a profound puzzle. If entropy always increases, then to have a universe with increasing entropy now, it must have started in a state of extraordinarily low entropy, a state of exquisite order. The early universe was not a chaotic mess. It was remarkably smooth and uniform, a hot, dense soup with matter and energy distributed almost perfectly evenly. This is a state of incredibly low entropy, the most improbable starting condition you could imagine. It is like finding all the air in a room spontaneously gathered in one corner, leaving a vacuum everywhere else. So why did the universe begin in such a special, ordered state? This is where our quantum fluctuations return as the cosmic architects. The pattern of those primordial ripples, the specific hot and cold spots imprinted on the cosmic microwave background, represents the initial microscopic seeds of disorder. But crucially, that disorder was minimal. The variations were tiny, only a few parts in 100,000. This specific, gentle pattern of quantum noise set the initial entropy of the cosmos at an astonishingly low value. It provided the single, definitive starting point from which everything could unfold. From that low entropy beginning, gravity began its work, pulling matter into galaxies and stars, transforming a smooth soup into a structured, complex cosmos. With every gravitational collapse, every star burning, every life form metabolizing, entropy increased. The arrow of time was launched. Without those specific quantum fluctuations creating that precise low entropy condition, the story would be different. If the early universe had been born in a state of maximum entropy, a state of complete thermodynamic equilibrium, nothing would ever happen. There would be no temperature differences to drive heat flow, no density contrasts for gravity to act upon. Time would have no direction. Past and future would be indistinguishable, a static, eternal soup where nothing changes and nothing is remembered. The universe would be in a state of heat death from the very beginning. So the arrow of time is not a fundamental law written separately. It is an emergent property, a consequence of a single, random quantum lottery ticket drawn at the dawn of everything. Our experience of a flowing, irreversible time of cause and effect, of memory and decay, hinges entirely on the gentle whisper of those first quantum jitters. We remember the past because it was more ordered, and that order was a gift from a random fluctuation in the first fraction of a second of existence. Our entire history, from the formation of stars to the thoughts in your mind, is the universe unwinding from that singular, improbable starting point, riding an arrow of time forged in quantum fire. But if the arrow of time is a single, unfolding story, what happens to all the paths not taken? Theory 14 offers a breathtaking, and some would say terrifying, answer. It suggests that every quantum fluctuation does not force a single choice upon reality. Instead, it causes the entire universe to split, birthing a new, parallel world for every possible outcome. This is the many worlds interpretation of quantum mechanics, a vision where our reality is just one thread in an infinite, ever-branching tapestry of alternate histories. To grasp this, let's revisit that troublesome electron in the double-slit experiment. In the standard interpretation, the electron exists in a superposition, a ghostly blend of all possible paths, until an observation forces it to randomly pick one, collapsing the wave function. The many worlds interpretation, proposed by physicist Hugh Everett in the 1950s, rejects this collapse entirely. Everett argued that the mathematics of quantum mechanics describes all possible outcomes as equally real. When the electron reaches the slits, the universe does not choose, it divides. In one newly created branch of reality, the electron goes through the left slit. In another, completely separate branch, it goes through the right slit. Both events happen with absolute certainty, but in worlds that are now forever disconnected. There is no randomness, only a continuous splitting of the cosmic whole. The observer is part of the system, too. So when a scientist looks at the detector, their own consciousness becomes entangled with the outcome. In one branch, the scientist sees an electron hit the left side of the screen and records that result. In the other branch, an identical copy of that scientist sees the electron hit the right side and records that. Both scientists are equally real, both convinced their outcome was the only one, unaware of the other's existence. Now apply this to the quantum vacuum. Every single virtual particle pair that flickers into existence is not a temporary loan from nothing. It is a permanent fork in the road of reality. In one world, the particle and antiparticle appear and annihilate. In another world, they appear and drift apart. In yet another, they appear and form a stable atom. Every possible fluctuation, no matter how improbable, actualizes somewhere. This process is not rare. It is constant and relentless. At every moment, at every point in space, the cosmos is undergoing a ceaseless mitosis, spawning uncountable new universes. This means the multiverse of eternal inflation is not just a collection of distant bubbles with different physical laws. It is a fractal tree of worlds nearly identical to our own, diverging with every quantum event. In a world that split from ours a second ago, you decided to take a different route to work. In another, a cosmic ray caused a mutation that changed the course of evolution. In another, the specific quantum fluctuation that made one region of the early universe slightly denser than another never happened, and our galaxy never formed. Every historical what-if, every choice you regret or celebrate, is not a lost possibility. It is a living reality in a parallel branch. The many worlds interpretation offers a strange comfort and a profound loneliness. It eliminates quantum randomness and the need for observers to collapse reality, painting a universe of pure, deterministic physics. But the cost is an existential solitude. Every triumph and tragedy is mirrored infinitely, rendering our choices both meaningless, because every version happens, and profoundly significant, because each version of us experiences its path as the only one. We are left to wonder if the quiet hum of the quantum field is not just the sound of creation, but the sound of the universe endlessly replicating itself, forever wondering what lies in the branches it left behind. The dizzying multiplicity of the many worlds interpretation offers one escape from quantum randomness, but it is not the only path. A far older idea suggests the dice were never truly thrown at all. This is Theory 15, pilot wave theory, also known as the de Broglie-Bohm interpretation, a radical and deterministic vision of the quantum world. In this view, The ghostly flickers of the vacuum are not random. Every particle has a definite position and trajectory at all times, guided by an unseen force, a hidden hand that steers the course of reality. The story begins not with uncertainty, but with a rebellion. In the 1920s, as the Copenhagen interpretation, with its inherent randomness and wave function collapse, became the dominant view, two physicists dared to propose a different path. Louis de Broglie, who first proposed that matter could behave as waves, and later David Bohm, who revived and expanded the idea, asked a simple, profound question. What if the quantum world is not fundamentally probabilistic? What if particles are real, tiny objects with precise locations, and the wave function is not a cloud of probability, but a real, physical wave that guides them? Imagine a tiny cork bobbing on the surface of a turbulent river. The cork has a definite position at every moment. You can, in principle, track its path. But its motion is not random. It is completely determined by the complex currents and eddies of the water flowing around it. In pilot wave theory, the particle is the cork. The pilot wave is the river, the famous wave function of quantum mechanics, that mathematical entity describing all possible states of a particle, is not a mere calculation tool. It is a real, invisible field that fills all of space, a fluid of information. This pilot wave does not tell the particle where it might be. It tells the particle exactly where to go. The particle rides the contours of this wave like a surfer on a precise, predetermined path. This elegantly explains the bizarre double-slit experiment without invoking superposition or collapse. A single electron fired at the slits is always a particle, but its guiding pilot wave passes through both slits, interferes with itself, and creates a complex interference pattern in the fluid of reality. The electron, following the precise instructions of this rippling wave, is steered to a specific point on the detector screen that aligns with the interference pattern. Run the experiment many times with identical starting conditions, and the electrons will always land in the same spots, building the pattern deterministically. The apparent randomness we see in standard quantum mechanics comes not from fundamental chance, but from our ignorance. We cannot know the exact initial position of every particle, what Bohm called the hidden variables. This ignorance forces us to use statistics, making the outcomes look random, even though beneath the surface, a strict causality reigns. So what does this mean for our quantum fluctuations? In this deterministic universe, the virtual particles dancing in the vacuum are not spontaneous, random creations. Their appearance and behavior are the direct, lawful consequence of the underlying pilot wave field. Their paths are set. The Casimir force pushing plates together is not a statistical pressure from random ghosts, but a deterministic force from a guided dance. This interpretation is philosophically staggering. It restores a classical sense of cause and effect to the subatomic realm. There is no true randomness, no dice playing God, no universe splitting with every decision. Reality is a single, unfolding story where everything that happens, from the formation of a galaxy to the firing of a neuron, was encoded in the initial conditions of the cosmos and the structure of the pilot wave. Yet, this comes at a profound cost. The theory is explicitly non-local. The pilot wave is instantaneous, connecting every particle in the universe in a hidden web of influence. A change in the wave function here can instantly affect a guided particle on the other side of the galaxy, seemingly violating the cosmic speed limit of light. For many physicists, this spooky action at a distance is too high a price to pay for determinism. Pilot wave theory remains a respected but minority view, a haunting reminder that our most successful theory might still be a shadow on the wall, and that the quantum vacuum's hum could be the sound of a hidden clockwork, ticking with a precision we have yet to fully hear. Determinism and hidden variables offer one escape from quantum chance, but they cannot explain the universe's most glaring omission. Our cosmos is filled with something we cannot see, a ghostly substance that outweighs all visible matter 5 to 1. This is dark matter, the invisible scaffold holding galaxies together, and its origin remains one of physics' greatest mysteries. Theory 16 proposes a radical solution. What if dark matter is not made of unknown particles, but is itself a fossil, a relic imprint of the universe's first quantum fluctuations? This idea suggests we look not beyond the standard model, but deeper into its most fundamental behavior. The proposal centers on a special class of hypothetical quantum fields. Most quantum fields, like the electromagnetic field, have fluctuations that average out to zero over time. Their positive and negative energy jitters cancel each other, leaving the vacuum energy we have discussed. But physicists speculate that certain exotic fields, with different intrinsic properties, might behave differently. Their quantum fluctuations might not cancel. Instead, these fields could have a non-zero average value that varies randomly across space, frozen in place during the universe's rapid expansion. Imagine a vast, invisible ocean with waves of all sizes. In a normal field, the crests and troughs average to a flat surface. In this exotic field, the waves could freeze in place, locking in a permanent, lumpy landscape of hills and valleys of energy. During the hot, dense early universe, these frozen quantum hills would have been regions of slightly higher energy density. And as we have seen, where there is more energy, gravity finds a foothold. As the cosmos cooled, these random lumps in the exotic field would have acted as supercharged seeds for gravitational collapse. Ordinary matter, made of protons and neutrons, was buffeted by intense radiation pressure in the early universe, preventing it from clumping until much later. But this proposed dark matter field, interacting only through gravity, would have felt no such pressure. Its frozen quantum fluctuations could have started clumping immediately after the Big Bang, long before normal matter could. These gravitational wells would then have drawn in the ordinary atoms, providing the ready-made templates for the first galaxies. In this view, the vast, diffuse halos of dark matter that envelop galaxies like ours are not swarms of discrete particles. They are the macroscopic manifestation of a single, primordial quantum field that jittered once long ago and never settled down. The field's random pattern, imprinted during inflation, became the cosmic blueprint for all structure. This offers a profound unification. The same quantum mechanism that seeded the visible galaxies with tiny density variations could also have created the dark matter halos that hold them together. One process, born from the quantum foam, would have sculpted both the visible and invisible architecture of the cosmos. It is an elegant idea, suggesting that the answer to the dark matter mystery has been hiding in plain sight, not as a new particle, but as a permanent tremor in the fabric of reality itself, a quantum whisper that gravity amplified into the silent skeleton of the universe. That silent skeleton of dark matter, born from frozen quantum whispers, implies a cosmos of immense age and scale. But within such an eternal, fluctuating expanse, a truly monstrous possibility emerges. In a universe governed by chance and probability, given enough time, anything that can happen will happen, no matter how absurd. This leads us to a thought experiment so unsettling it threatens to unravel our entire understanding of existence. It is the paradox of the Boltzmann brain. The idea is named for Ludwig Boltzmann, the 19th century physicist who helped develop statistical mechanics and our understanding of entropy. He grappled with how our ordered universe could arise from chaos, suggesting it might be a rare but inevitable statistical fluctuation in a much larger, eternal, and mostly disordered reality. Modern cosmology has taken this seed and grown a terrifying tree. In a truly eternal universe, or in an eternally inflating multiverse where space and time go on forever, quantum fluctuations are not just a feature of the early cosmos. They are an endless, permanent process. Given infinite time, every possible arrangement of particles will eventually occur by random chance. This includes the arrangement of particles that constitutes a fully formed, self-aware human brain, complete with false memories of an entire life, floating in the void. According to pure probability, it is vastly more likely for a single, conscious brain to spontaneously fluctuate into existence from the quantum foam than for an entire 13.8 billion-year-old universe with galaxies, planets, and billions of conscious beings to evolve in perfect order. The math is brutally clear. The entropy of a single brain is much lower than the entropy of our entire complex cosmos. In an eternal sea of maximum disorder, a small, ordered fluctuation like a brain is statistically far more probable than a gigantic, ordered fluctuation like our universe. So, if you believe the cosmos is eternal and quantum randomness reigns, you are forced into a horrific conclusion. You are far more likely to be a Boltzmann brain, a momentary flicker of consciousness in the dark, than a person who evolved on a planet in a vast, ancient universe. All your memories, your knowledge of physics, your sense of a past and a future would be nothing but an elaborate, convincing illusion generated by a random accident. This is not just a philosophical puzzle. It is a direct challenge to modern cosmology. If our best theories predict that observers like us should almost certainly be Boltzmann brains, then those theories are almost certainly wrong. Physicists see this paradox as a valuable, if disturbing, guide. It places strict limits on what our models of the universe can allow. A viable cosmology must make the existence of ordinary observers like us vastly more probable than the spontaneous generation of disembodied brains. This has led to serious reevaluations of ideas like eternal inflation. Perhaps the multiverse is not truly eternal. Maybe universes like ours are common in the landscape, making our kind of ordered evolution the norm, not the freak accident. Or perhaps the universe has a definite beginning and will have a definite end, bounding time and limiting the window for such monstrous fluctuations to occur. The Boltzmann brain paradox forces us to confront the deepest questions of evidence and existence. How do you know you are not a brain that formed 5 minutes ago with false memories? You cannot prove you are not, but if that were true, science itself would be meaningless, as all data and logic would be unreliable phantoms. To do science, we must assume our senses and memories connect to a real, ordered, shared history. The paradox, therefore, is a warning from the abyss of probability. It tells us that a universe without structure, without an arrow of time, without a definitive history, is a universe where knowledge and consciousness are impossible illusions. Our very ability to ponder this idea may be the strongest evidence that we are not ghosts in the quantum void, but products of a cosmos with a real, singular story, one where the fluctuations were just chaotic enough to create us, but not so chaotic as to make our existence a statistical absurdity. Escaping the paradox of the Boltzmann brain requires a cosmos with a definitive story, but perhaps that story is not a single, linear tale. It could be a chapter in an endless book, where the final page of one volume becomes the blank first page of the next. This is Theory 18, Conformal Cyclic Cosmology, a breathtaking vision proposed by the Nobel laureate Roger Penrose. It suggests our universe is not the first, nor will it be the last. It is one aeon in an infinite, unbroken chain, and the bridge between these cosmic epochs is built from the subtle vibrations of quantum fields. To understand this radical idea, we must journey to the far, far future, trillions upon trillions of years from now. In this distant era, the accelerating expansion driven by dark energy will have done its work. All galaxies will have vanished over the cosmic horizon, leaving not even a faint glow in the sky. Every star will have burned out. Every black hole will have evaporated through Hawking radiation, and every proton, the very building block of atoms, will have decayed into radiation. What remains is a universe of almost perfect nothingness, a vast, cold, and nearly empty expanse filled only with a thin, uniform sea of massless particles like photons and gravitons, all stretched to unimaginably long wavelengths by their relentless expansion. This is a state of maximum entropy, a cosmic heat death where time, in any meaningful sense, seems to have lost its direction. In this desolate, smooth, and featureless end, Penrose sees a new beginning. He focuses on a profound symmetry in physics known as conformal invariance. When all particles are massless and the universe is stretched to an almost infinite scale, the concepts of distance and time lose their absolute meaning. A universe that is infinitely large and infinitely old can be mathematically rescaled, or conformally transformed, to look exactly like a universe that is infinitely small and infinitely young. In this strange, scale-free geometry, the endless, cold emptiness of the far future becomes indistinguishable from the hot, dense singularity of the Big Bang. They are two sides of the same conformal coin, but for a new aeon to ignite, this smooth, dead universe needs a seed of structure, a reason to differentiate. This is where quantum fluctuations make their grand, cyclical return. In the otherwise perfect smoothness of the end-time universe, the massless fields that remain, like the gravitational field, still experience quantum jitters. These are tiny, random variations in the field's energy, the last whispers of uncertainty in a fading cosmos. Penrose proposes that these fluctuations do not fade away. Instead, as one aeon conformally transforms into the next, these quantum tremors in the gravitational field are translated, rescaled, and amplified. They become the primordial density variations in the hot, dense fireball of the next Big Bang. The gentle quantum ripples in the graveyard of one universe become the explosive seeds for the galaxies of the next. In this view, the cosmic microwave background radiation, that fossilized map of our universe's infancy, is not just an imprint from our own beginning. It may also carry a faint, encoded signature, a gravitational wave echo from the entire history of the eon that came before ours. Our universe's structure, and thus our very existence, could be the direct inheritance of quantum fluctuations that stirred in the dying embers of a previous cosmic cycle. Conformal cyclic cosmology paints a picture of eternity not as a static void, but as an endless, breathing rhythm of creation and dissolution, where the quantum hum never ceases, only transforms, ensuring that from the ashes of absolute silence, a new symphony of matter and life will always, inevitably, begin again. The endless rhythm of cosmic rebirth hints at a universe stitched together by deeper, hidden threads. If one eon can transform into the next, perhaps the fabric of space itself is not a smooth continuum, but a tapestry of invisible connections. This brings us to a theory so elegant it unites the two greatest puzzles in physics with a single, breathtaking equation. It is the ER equals EPR conjecture, a proposal that the spooky link of quantum entanglement is actually held together by tiny subatomic wormholes. To grasp this, we must meet the two halves of this cosmic equation. EPR stands for Einstein, Podolsky, and Rosen, the physicists who, in 1935, first highlighted the bizarre nature of quantum entanglement. They described a pair of particles linked in such a way that measuring the state of one instantly determines the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, a violation of locality that seemed to suggest information traveled faster than light. The other half, ER, stands for Einstein and Rosen, who that same year published a paper with Nathan Rosen describing a theoretical bridge connecting two distant points in spacetime. This Einstein-Rosen bridge is what we now commonly call a wormhole, a shortcut through the fabric of the universe. For decades, these two ideas, entanglement and wormholes, lived in separate worlds. Entanglement was a quantum mystery, while wormholes were a speculative feature of general relativity, the theory of gravity. They were described by entirely different mathematical languages. Then, in 2013, physicists Juan Maldacena and Leonard Susskind made a radical proposal. What if EPR and ER are not just connected? What if they are the same thing? The ER equals EPR conjecture posits that every pair of entangled particles is not mysteriously linked across empty space. They are linked because they are physically connected by a microscopic wormhole, an Einstein-Rosen bridge too tiny to traverse, but real in the geometry of spacetime. In this view, entanglement is not a ghostly correlation. It is architecture. It is the physical stitching of the universe. When two particles become entangled, a Planck-scale wormhole forms between them, binding their fates together through a literal tunnel in the fabric of reality. This has a staggering implication for the quantum foam. That seething, turbulent froth at the smallest scales is not just a chaotic mess of virtual particles. It could be a dynamic, ever-changing network of these microscopic wormholes, constantly forming, breaking, and reforming. Each fleeting virtual particle pair might be connected by a transient wormhole, a tiny bridge that snaps shut as the particles annihilate. The vacuum itself, with all its fluctuations, could be a dense, knotted web of entanglement, woven together by an unfathomable number of these geometric threads. This idea offers a potential path to unify quantum mechanics and gravity, the holy grail of physics. Gravity, in Einstein's theory, is the curvature of spacetime. Quantum mechanics describes the behavior of particles and fields. ER equals EPR suggests that the curvature, the very geometry of spacetime, emerges from the quantum entanglement of the underlying fields. Space is not a fundamental stage. It is a consequence of connectivity. Where there is no entanglement, there is no space. This gives us a profound new way to visualize the universe. The three-dimensional world we experience may be a holographic projection, as we discussed earlier, but the pixels of that projection are not just bits of information. They are entangled qubits, connected by a labyrinth of wormholes. The smooth, classical geometry we see is the average, large-scale result of this frenetic quantum weaving. It is as if the cosmos is a vast, cosmic brain, where each neuron is a quantum of space, and the thoughts it thinks are the stars and galaxies, arising from the connections between them. So the next time you hear about the spookiness of entanglement, picture not an invisible signal, but a hidden tunnel, a thread in the cosmic tapestry. The quantum fluctuations that birth particles and shape galaxies might be the tremors along these threads, the vibrations of a universe whose true nature is not substance, but connection. The hidden tunnels of entanglement suggest a universe woven from connection, not substance. Yet this breathtaking vision collides with a fundamental rift in our understanding of reality. The 20th theory confronts the greatest unsolved problem in physics, the quest for a theory of quantum gravity. For over a century, we have lived with two magnificent but incompatible descriptions of the cosmos. Quantum mechanics rules the domain of the very small, describing particles and forces with breathtaking precision, but within a fixed, passive stage of space and time. General relativity rules the domain of the very large and massive, describing gravity not as a force, but as the dynamic curvature of that very stage itself. Both theories are spectacularly successful, yet they speak different mathematical languages and obey different rules. Where they meet, at the center of a black hole or the first instant of the Big Bang, our equations break down into infinities called singularities, points where density and curvature become infinite and physics simply stops making sense. This is not just a mathematical inconvenience. It is a screaming signal that we are missing the true, unified picture. The core of the conflict lies in how each theory views the fabric of reality. In quantum mechanics, everything is granular, discrete, and probabilistic. Energy comes in packets. Fields jitter with uncertainty. In general relativity, spacetime is smooth, continuous, and deterministic, a flexible fabric that bends and warps. To unite them, we must answer a deceptively simple question. What happens to spacetime itself when we zoom down to the quantum scale? Does it remain a smooth continuum, or does it finally reveal its granular, quantum nature? Two leading candidates offer radical and very different answers. The first is loop quantum gravity. In this approach, there is no background stage. Space is not a container things sit in. It is a network of relationships, a fabric woven from tiny, finite loops of gravitational field, often visualized as a spin network. These loops are the quanta of space, the smallest possible pieces of area and volume. You cannot have half a loop, just as you cannot have half an electron. Space is not infinitely divisible. It is made of discrete, woven threads. In this granular geometry, the concept of a singularity vanishes. As matter collapses under gravity, reaching incredible densities, these loops of space become so tightly packed that they generate a tremendous repulsive force, a quantum pressure from the geometry itself. Instead of collapsing to an infinite point, the collapsing matter rebounds. A black hole could become a gateway to another region of spacetime, or a dying universe could bounce into a new Big Bang. Here, quantum fluctuations are not just happening in spacetime. They are the fluctuations of spacetime. The very threads of the cosmic fabric vibrate and change their connections, meaning distances and volumes themselves are subject to quantum uncertainty. The other grand framework is string theory. It proposes that the fundamental ingredients of reality are not point-like particles, but incredibly tiny, vibrating strings. Different vibrations correspond to different particles, like notes on a guitar string. In this view, gravity arises from a particular string vibration, the graviton. But for the mathematics to work, strings must move through a spacetime with more than the 3 dimensions we experience. The extra dimensions are curled up or compactified at scales far smaller than an atom. In string theory, spacetime itself may emerge from the collective behavior of strings and higher dimensional objects called branes. The fluctuations of the quantum vacuum are the vibrations of these strings, and the geometry of spacetime is a dynamic, evolving consequence of their interactions. Crucially, string theory also suggests a minimum length scale, preventing the infinite collapse of a singularity. Both theories, in their own way, paint a picture where the smooth stage of general relativity is an illusion, a calm surface over a deep quantum ocean. At the Planck scale, spacetime is a stormy foam of probabilistic geometry. There is no here or now in a definite sense, only probabilities of connection. This means the very ideas of before and after, of cause and effect, may break down at this fundamental level. A quantum fluctuation might not just create a particle. It might momentarily twist the local network of spacetime loops, or cause a string to vibrate in a way that subtly warps an extra dimension. In such a reality, the Big Bang was not a singularity, but a quantum phase transition, a moment when the geometry of the previous state fluctuated into a new configuration, blossoming into our expanding cosmos. The search for quantum gravity is the search for the grammar of these geometric fluctuations. It is an attempt to hear the true language of the vacuum, a language where the words are not particles or forces, but the vibrating, fluctuating atoms of space and time themselves. The universe's quantum tapestry is woven from ceaseless change, but what if the very act of watching could make the threads stand still? This is the quantum Zeno effect, a phenomenon where observation does not just reveal reality, it actively stifles it. Named after the ancient Greek philosopher Zeno of Elea, who proposed that a flying arrow must be motionless at every instant, the effect reveals a startling truth about the quantum world. An unstable particle, like a radioactive atom waiting to decay, exists in a superposition. It is both intact and decayed, a ticking quantum clock. According to the rules, the probability of it decaying increases over time. But if you constantly measure it, asking over and over again, "Have you decayed yet?" something bizarre happens. The frequent, repeated observations reset the particle's internal quantum clock, forcing it back to its initial, intact state. The more often you look, the less likely it is to change. You can, in effect, watch a particle into permanence, freezing its natural quantum evolution. It is not that time stops, but that the system is denied the opportunity to evolve freely between measurements. The quantum fluctuations that would normally drive its change are suppressed by the relentless gaze of an observer. Now, scale this idea up from a single atom to the entirety of existence. In the first moments of the cosmos, the universe was a seething quantum foam, a superposition of every possible configuration, fluctuating wildly. According to some interpretations of quantum mechanics, it required an observation to collapse this frenzy into one concrete reality. But what if the process was more nuanced? What if a universal observer, perhaps a cosmic consciousness, or the combined act of measurement from all future conscious beings, did not just make a single choice? What if, through a grand, cosmological version of the quantum Zeno effect, this observation continuously pinned the universe into a particular stable state? The most violent fluctuations, those that would have torn reality apart or led to a completely different set of physical laws, were constantly measured and suppressed, frozen out of existence. The gentle, viable fluctuations that allowed for galaxies and life were the ones permitted to evolve. In this speculative view, our stable, classical reality is not the default. It is a carefully maintained artifact, a garden cultivated by observation, where the weeds of catastrophic quantum change are constantly plucked by the act of witnessing. It suggests that stability itself is an achievement, a dynamic equilibrium sustained against a background of infinite chaos. The quiet hum of the universe we perceive might be the sound of a quantum system that has been watched into stillness, its most dangerous potentials forever held at bay by a gaze we do not yet understand. The stability we take for granted could be the universe's most dangerous illusion. This brings us to a theory of cosmic doom so absolute it makes black holes seem gentle. It is the idea of vacuum decay, and it suggests our entire reality is resting in a state of precarious, temporary peace. To understand this existential threat, we must think of the universe's vacuum not as empty, but as a field sitting in a valley of energy, like a ball resting at the bottom of a bowl. This is its lowest energy state, its most stable configuration. Physicists call this the true vacuum, but what if our cosmic ball is not in the deepest valley? What if it is resting in a shallower dip on a much larger hillside, a local minimum? This is a false vacuum. It appears stable. You can jostle the ball, and it will roll back to the bottom of its little dip. It can stay there for billions of years, just as our universe has. But somewhere out on that hillside, there is a far deeper valley, a state of vastly lower energy. That is the true vacuum. The terrifying possibility is that our universe, with all its specific laws and constants, exists in this false metastable state. The quantum fields that govern reality are not in their absolute lowest energy configuration. They are trapped, and quantum mechanics provides the escape route. Through a random, large quantum fluctuation, the field could tunnel through the energy barrier of its local dip. In one tiny region of space, the ball would suddenly find itself on the other side of the hill, beginning a catastrophic roll down into the deeper valley. That region would become a bubble of true vacuum. Inside this bubble, the laws of physics would be completely different. The fundamental constants that dictate the strength of forces, the mass of particles, even the number of spatial dimensions would be rewritten. Atoms could not hold together. The very structure of matter would dissolve. This bubble would not sit still. Its walls, the boundary between the false vacuum of our universe and the new true vacuum inside, would expand in all directions at the speed of light. Nothing could outrun it. As it expands, it would convert every bit of the old universe it touches into the new alien reality. The process would release an unimaginable amount of energy, a wall of destruction that would erase everything in its path: galaxies, stars, planets, every structure held together by the old laws. From our perspective, there would be no warning. One moment, the universe would be as it is. The next, a sphere of pure annihilation would appear from a single point and engulf everything at light speed. We would not see it coming because the signal of its arrival would be the event itself. This is not science fiction. It is a legitimate, albeit speculative, consequence of our best models of particle physics, particularly when we consider the measured mass of the Higgs boson. The equations suggest our vacuum might indeed be metastable. The good news, if you can call it that, is that the probability of such a tunneling event happening in any given region of space in any given year is astronomically small. The expected lifetime of our false vacuum could be many, many times the current age of the universe. But in an infinite cosmos or an eternal multiverse, given enough time and enough space, probability becomes a promise. Somewhere, at some point, a quantum fluctuation could punch a hole in the fabric of our reality, and the end would begin. It is the ultimate reminder that the quantum hum is not just the sound of creation, but a constant, random search for a deeper silence. a final stability that would erase us from existence in the blink of a cosmic eye. Yet even the threat of vacuum decay implies a universe where structure can exist long enough to be erased. That structure reaches its most exquisite form in the living cell, a realm of staggering complexity governed by chemistry. But could the quantum world's signature randomness reach into biology itself, influencing the very origin of life? This is a profound speculation, a bridge between the subatomic and the living. The traditional story of life's beginnings involves chemistry in a primordial soup, random combinations of molecules over vast stretches of time. But randomness at the chemical level is not truly random in the quantum sense. It is classical randomness, like the chaotic tumbling of dice. Quantum randomness is different, more fundamental. It is the inherent unpredictability written into the fabric of reality. Could that deeper randomness have played a role? One fascinating area of study is quantum biology, which examines whether quantum effects are not just present in, but essential for living systems. We already see hints. In photosynthesis, the process plants use to turn sunlight into energy, experiments suggest that quantum coherence may be at work. Energy from an absorbed photon does not take a single path through the complex molecules of the photosynthetic apparatus. It explores multiple pathways simultaneously, like a wave, to find the most efficient route to the reaction center. This quantum search algorithm, lasting only femtosecons, allows for astonishing efficiency. This is a quantum process happening inside a warm, wet, messy living cell, not in a frozen lab. If quantum effects can optimize energy transfer, could they have also guided the earliest, most improbable steps toward life? Consider the puzzle of homochirality. Many biological molecules, like the amino acids that build proteins, come in two mirror image forms, left-handed and right-handed. Life on Earth uses almost exclusively left-handed amino acids and right-handed sugars. Why this specific choice? A classical random process would produce a 50-50 mix. Something must have broken the symmetry. One compelling theory points to a subtle interaction between molecules and polarized light, where the weak nuclear force, a fundamentally quantum force, creates a tiny energy difference between the mirror forms. Over immense time, this minuscule quantum bias, amplified by cycles of crystallization and dissolution, could have tipped the scales toward the handedness we see. The seed of life's asymmetry may have been a quantum fluctuation, amplified by chemistry. More radically, we can look at the engine of evolution itself, genetic mutation. Mutations arise from errors in copying DNA, often caused by environmental damage like radiation. But some mutations may have a quantum origin. The bonds that hold the rungs of the DNA ladder together are governed by the probabilistic rules of quantum mechanics. A proton, part of a hydrogen bond, can sometimes tunnel from one position to another, briefly creating a mismatched pair. Usually, cellular repair mechanisms fix this. But occasionally, such a quantum tunneling event could lead to a permanent mutation, a change in the genetic code. This is not science fiction. Quantum tunneling is a well-established part of enzyme catalysis, helping reactions that would be impossibly slow otherwise. If quantum tunneling can help enzymes function, it is plausible it could also, very rarely, cause the errors that drive change. In this view, the raw material for natural selection, genetic variation, is not just provided by cosmic rays or chemical accidents. It is also supplied, in a very small but persistent way, by the ghostly tunneling of particles within the molecule of life itself. The quantum vacuum's tremors, translated through chemistry into a proton's jump, could write a new letter in the book of heredity. This leads to a staggering possibility. The first self-replicating molecule, the ancestor of all life, may have assembled not just through classical chance, but through a series of quantum-assisted steps. A quantum fluctuation in an electron cloud might have made a chemical bond just stable enough to form. A tunneling event might have allowed a crucial reaction to proceed in the cold depths of a primordial ocean or on the surface of a clay mineral. The leap from non-life to life is the greatest statistical improbability on Earth. Quantum mechanics, with its allowance for tunneling and superposition, provides a toolkit for bypassing classical energy barriers, for making the impossible merely improbable. It offers a physical mechanism for the luck that life required. So while we cannot say quantum fluctuations created life, we can seriously ask if they were an essential collaborator in the process. The same fundamental unpredictability that seeded galaxies may have also nudged the first protocell toward replication. From the cosmic to the microscopic, the quantum whisper seems to be a universal author, writing not only the laws of physics and the story of the stars, but perhaps, just perhaps, the first chapter of our own biological story. The universe's quantum whispers might not be random offers, but the echoes of a conversation across time itself. This is the transactional interpretation, a radical view that restores symmetry to the quantum world by suggesting the future talks back to the past. Forget the standard story of a particle existing in a fuzzy superposition until an observation in the present collapses it into reality. In this model, proposed by physicist John Cramer, every quantum event is a negotiation, a closed loop completed by a handshake between waves traveling forward and backward in time. It begins with an emitter, like an excited atom ready to release a photon. This emitter sends out an offer wave. This wave is not a particle, but a probability wave that radiates outward in all directions, forward in time, exploring every possible path to a potential absorber, like another atom ready to receive the energy. When this offer wave encounters a suitable absorber, something remarkable happens. That absorber responds by sending a confirmation wave backward in time, retracing the exact path of the original offer wave back to the emitter. Only when the emitter receives this confirmation, this echo from the future, is the transaction completed. The handshake is sealed. At that moment, the probability wave collapses, and we see a real, tangible particle, the photon, having traveled a definite path between the 2 points. The particle we detect is not a thing that existed independently along the way. It is the momentary standing wave, the reinforced vibration, created where the offer wave from the past and the confirmation wave from the future meet and reinforce each other. This creates a self-consistent loop in time, where the effect, the absorber's readiness, helps confirm the cause, the emitter's decision to send the offer. So what does this mean for the ghostly dance of the quantum vacuum? In this timeless framework, those virtual particles flickering in and out of existence are not spontaneous random creations. They are uncompleted transactions, offers sent out by the vacuum that do not find a confirming handshake from a suitable absorber. They are half-finished conversations that fizzle out because no one answers the call from the future. The famous Casimir effect, where plates are pushed together by vacuum pressure, arises because the space between the plates restricts which offer waves can fit. Fewer possible transactions can be completed in that narrow gap compared to the outside, creating a net force. Even more profoundly, this interpretation elegantly explains the spooky results of the double-slit experiment without invoking multiple worlds or conscious observers. A single electron emitted toward the slits sends out its offer wave, which goes through both slits and interferes with itself. That complex, interfering offer wave reaches a detector on the far screen. The specific pixel on the detector that is ready to absorb the electron then sends its confirmation wave back through time. That confirmation wave retraces the interfering paths, selectively reinforcing only one of them, guiding the transaction to completion at that specific point. The electron was never a particle in flight. It was a completed handshake along a path that only became definite once the entire loop, from past emitter to future absorber and back again, was established. This paints a universe where the present moment is not a knife edge between a fixed past and an open future. It is a nexus of countless handshakes, a tapestry woven from threads that stretch both backward and forward in time. The quantum fluctuations we perceive as the fundamental noise of reality are the constant hum of these offers and negotiations, a cosmic marketplace where every transaction requires agreement from both ends of time. It suggests a deep, hidden order beneath the apparent randomness, a universe where every event, from the decay of an atom to the twinkle of a star, is a collaborative act between what was and what will be. The universe's hidden conversations across time hint at a deep underlying order, a symmetry we have yet to fully witness. But what if that order is so profound, it doubles the entire cast of particles in existence? This is the promise of supersymmetry, a beautiful and elegant theory that proposes a fundamental partnership at the heart of reality, one that could finally tame the vacuum's furious energy. Supersymmetry, often called SUSY for short, suggests that for every particle we know in the standard model, there exists a hidden twin, a superpartner. For every quark, there is a squark. For every electron, a selectron. For every photon, a photino. These superpartners are not mere copies. They have a crucial defining difference. If the known particles are matter particles or fermions, their superpartners would be force carriers or bosons, and vice versa. This creates a perfect symmetry between matter and force, a dance where every dancer has a mirror partner from the opposite class. This symmetry is so powerful it could solve our greatest embarrassment, the vacuum catastrophe. Remember that staggering calculation, where the quantum fluctuations of all known fields add up to an energy density 120 orders of magnitude too large. The problem arises because the contributions from bosons and fermions to the vacuum energy are opposite in sign. Bosonic fluctuations push the energy positively, while fermionic fluctuations pull it negatively. In our incomplete standard model, these contributions do not cancel. They run wild, adding up to that monstrous universe-breaking number. Supersymmetry offers a breathtakingly neat solution. If every boson has a fermionic superpartner and every fermion has a bosonic superpartner, then for every positive fluctuation from a particle, there is an exactly opposite, negative fluctuation from its twin. In a perfectly supersymmetric universe, these contributions would cancel out perfectly, leaving the vacuum energy at zero, or at least at a value small enough to match our observations of dark energy. The quantum foam would be calmed, its most violent tendencies neutralized by this exquisite balance. The vacuum catastrophe would simply vanish, replaced by a serene and stable foundation. This cancellation is more than mathematical trickery. It suggests that the seething chaos of the quantum vacuum we perceive is just a broken remnant of a far more harmonious state. At the incredibly high energies of the early universe, supersymmetry would have been unbroken. Particles and their superpartners would have had identical masses. and their fluctuations would have danced in perfect, annihilating harmony. The vacuum would have been quiet, stable, and symmetrical. As the universe cooled and expanded, this perfect symmetry broke. The superpartners gained much larger masses, becoming too heavy to be produced in our current low-energy world. Their balancing influence withdrew, leaving behind the unruly vacuum energy we struggle to calculate today. Finding evidence for these superpartners would not just add new particles to a chart. It would reveal that our reality is a faded, asymmetric shadow of a more perfect, balanced, and stable cosmic order. It would show that the quantum fluctuations shaping our world are the echoes of a broken symmetry, the leftover noise from a time when every particle had a twin, and the void was truly at peace. Yet this search for a deeper cosmic symmetry forces us to confront a fundamental limit. There is a maximum amount of information any region of space can contain, a cosmic speed limit for computation. This boundary is defined by the physics of the most extreme objects we know, leading to a staggering theory. The most powerful and efficient computer the laws of physics will allow is not a silicon chip, but a black hole. Its processor is the event horizon, and its code is written in the language of quantum fluctuations. This idea stems from Jacob Bekenstein's groundbreaking work, which revealed that a black hole's entropy, its hidden information, is proportional to the area of its horizon, not its volume. This is the Bekenstein bound, a universal law stating that the maximum information you can store in any region of space is directly related to the surface area enclosing it. Think of it like a cosmic hard drive. For a normal object, like a book or a hard drive, the amount of information it can hold grows with its volume. But for a black hole, the ultimate data cruncher, information capacity scales with its surface area. This is a profound clue about the nature of reality, hinting again at the holographic principle. Now, combine this with the work of physicists like Seth Lloyd, who explore the ultimate physical limits of computation. Lloyd calculated the maximum number of logical operations a system with a given mass and size can perform. The result is astonishing. When you configure matter to compute at the absolute limits allowed by quantum mechanics and relativity, the most efficient arrangement is to let it collapse into a black hole. A black hole processes information at the maximum possible speed, the Planck rate, by exploiting the quantum fluctuations at its event horizon. Each tiny Planck-sized area of the horizon can be thought of as a single bit, flickering between 1 and 0 as virtual particles pop in and out of existence. The entire horizon is a frenzied, two-dimensional quantum processor, performing an unimaginable number of calculations per second as it scrambles and transforms the information of everything that falls inside. In this view, Hawking radiation is not random thermal noise. It is processed output, the result of a colossal computation where the information of infalling matter is chaotically mixed and eventually emitted, transformed, but not destroyed. The black hole is not a destroyer of information, but the universe's ultimate computer, running the most complex encryption algorithm possible. This leads to a breathtaking, almost recursive possibility. If black holes are optimal computers, and our universe gave rise to black holes, could the cosmos itself be a computational system? Perhaps the universe is not just like a computer. Perhaps it is a vast, physical system processing information according to the rules of quantum mechanics and general relativity. The quantum fluctuations that seeded galaxies, the entanglement that weaves space together, the evolution of fields over time, all of this could be seen as a cosmic computation. In this framework, the laws of physics are not just descriptive equations. They are the operating code. The initial conditions of the Big Bang were the input data, and the unfolding history of stars, planets, and life is the running output. The universe computes itself into existence, moment by moment, with every quantum fluctuation representing a fundamental logical operation. This does not imply a programmer in the sky. It suggests that computation is a fundamental physical process, as basic as energy and entropy. To be, in this view, is to compute. The quiet hum of the quantum vacuum is the sound of the universe thinking, calculating its own next state in an endless, breathtaking sequence of steps that began with a single random bit. The universe computing its own existence leads to an inevitable question. If reality is a quantum calculation, where does the calculator reside? Theory 27 ventures into the most intimate frontier of all, proposing that the very seat of human consciousness might be a quantum computer, sensitive to the whispers of the cosmos. This is the theory of orchestrated objective reduction, a bold and deeply controversial idea proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that consciousness is not an emergent property of classical brain computation, like software running on the wetware of neurons. Instead, it is a fundamental feature of the universe, rooted in the physics of quantum gravity, and it happens in structures inside our brain cells called microtubules. Microtubules are tiny, cylindrical scaffolds that form part of the skeleton of neurons and other cells. Penrose and Hameroff propose that these structures are not just passive supports. They are exquisitely crafted to isolate and protect quantum states. Within them, proteins called tubulins could exist in a superposition of states, a quantum coherence, much like the famous cat that is both alive and dead. This quantum coherence could spread across vast networks of neurons, creating a unified quantum field within the brain. But a superposition cannot last forever. According to Penrose, it would naturally collapse due to a process he calls objective reduction, a self-collapse driven by the underlying geometry of spacetime itself, linked to quantum gravity. The specific pattern of this collapse, the way the superposition chooses one state over all others, is not random. It is orchestrated by the biochemical architecture of the microtubules. And this orchestrated collapse, this moment of quantum decision-making, is what we experience as a moment of conscious awareness. Each flicker of thought, each qualia of sensation, corresponds to a quantum gravitational event inside your neurons. Now, weave this into the cosmic tapestry we have been exploring. If consciousness is a quantum gravitational process, then it is inherently connected to the fundamental fabric of reality. The same quantum fluctuations that seed galaxies and hum in the vacuum are not separate from the fluctuations happening in the microtubules of your brain. They are part of the same universal field. This leads to a staggering possibility: the gentle tremors of the cosmic quantum foam, the echoes of inflationary ripples, or even the subtle influence of distant gravitational waves, could theoretically interact with these delicate brain-bound superpositions. Our conscious thoughts, our moments of intuition or creativity, might not be sealed off from the universe. They could be subtly nudged, modulated, or synchronized by the background quantum noise of reality itself. In this view, the brain is not a closed system. It is a resonant quantum antenna tuned to the hum of spacetime. A moment of profound insight might not just be a novel neural connection. It could be a moment of quantum coherence in your microtubules, aligning with a particular pattern in the universal field. Of course, this theory exists at the very edge of mainstream science. Critics point out that the warm, wet, noisy environment of the brain seems utterly hostile to maintaining fragile quantum states, which we can only preserve for fractions of a second in supercooled laboratory conditions. The evidence for quantum processes in cognition remains hotly debated, yet the idea persists as a profound philosophical proposition. It suggests that our inner world of consciousness and the outer cosmos of quantum fluctuations are not separate realms. They may be different expressions of the same underlying physics. We are not just observers of the quantum universe. We may be its most intimate artifacts, with the silent symphony of our thoughts composed in the same key as the first vibrations of the Big Bang. This deep connection between mind and cosmos points to a reality far more unified than it appears. Our 28th theory suggests that the quantum fluctuations we have been exploring are not the fundamental level of existence. They are surface ripples, hints of a far deeper, hidden ocean of reality. This is the theory of the implicate order, proposed by physicist and philosopher David Bohm. Bohm was deeply dissatisfied with the fragmented, probabilistic picture of the universe presented by standard quantum mechanics. He saw a world of separation, where particles are treated as isolated objects, and the act of observation violently collapses possibilities into a single fact. He believed this was not a true description of nature, but a reflection of our own fractured way of thinking. In response, he proposed a radical, holistic vision. Beneath the world we perceive, Bohm suggested, lies the implicate order. The word implicate means enfolded or woven together. This is a realm where everything is connected, where the entire universe exists in a state of undivided wholeness. There is no separation between objects, no clear distinction between here and there, no linear flow of time as we know it. All of space, all of history, and all potential futures are folded into this single, seamless fabric. From this implicate order, our everyday reality unfolds. Bohm called this the explicate order. This is the world of separate objects, definite locations, and linear time. The world of tables, chairs, galaxies, and quantum particles that appear to jump randomly. The process of unfolding is continuous and dynamic, like a ceaseless projection of a deeper, more complex reality onto the screen of our senses. So where do quantum fluctuations fit into this? In Bohm's view, the strange behavior of particles, their superposition, their entanglement, their apparent randomness are not primitive facts. They are artifacts, side effects of the unfolding process. A quantum fluctuation is not a spontaneous creation from nothing. It is a ripple, a tiny unfolding, from the implicate order into the explicate. When a virtual particle pair appears, it is not popping into existence in a void. It is a momentary manifestation of a relationship that already exists in the enfolded whole. The famous spooky action of entanglement, where particles remain connected across vast distances, makes perfect sense in this framework. Those particles are not sending signals faster than light. They are simply different aspects of the same underlying implicate reality, unfolding in a correlated way. Their connection is not transmitted. It is pre-existing, woven into the fabric of the whole. To grasp this, think of a simple analogy. Imagine a droplet of ink dropped into a viscous liquid like glycerin. If you slowly stir the liquid with a rod, the ink droplet will be stretched out into a long, thin thread, eventually becoming so finely dispersed that it becomes invisible to the eye. The ink is now enfolded or implicate within the glycerin. Now reverse the stirring. As you turn the rod the other way, the thread of ink will slowly gather back together, coalescing into a single, visible droplet once more. The droplet has been unfolded or explicated. In this analogy, the entire invisible thread is the implicate order. The single droplet you see at the beginning and the end is the explicate order. The process of stirring is the dynamic relationship between them. A quantum fluctuation is like a tiny, temporary reversal in the stirring, a moment where a bit of the invisible thread briefly becomes visible before being enfolded again. Bohm believed this model could resolve the paradox of the observer. In his view, consciousness itself is not separate from the implicate order. It is a high-level expression of it. The human mind, with its capacity for intuition and insight, can directly apprehend this deeper level of reality. When we perceive wholeness, when we have a flash of creative understanding that seems to come from nowhere, we are not just processing neural data. We are momentarily tapping into the implicate order itself. Our observations do not collapse a wave function. They participate in the unfolding. This means the constant buzz of the quantum vacuum is not meaningless noise. It is the visible tremor of an infinite, unfolding creation. Every virtual particle, every flicker of energy, is a word spoken from a deeper language, a language where the speaker and the listener, the observer and the observed, are one and the same. The universe is not a collection of things, but a single dynamic verb, a process of perpetual enfolding and unfolding. And we, with our quantum-sensitive minds, are not just watching the show. We are that process, becoming aware of itself. That profound sense of cosmic unity might be the deepest truth, but our daily reality feels solid, definite, and shared. How does the fuzzy, probabilistic quantum world, buzzing with infinite possibilities, crystallize into the single, objective universe we all agree upon? The answer may lie in a process of cosmic natural selection, where the environment itself acts as the judge. This is the theory of quantum Darwinism. It proposes that the classical world we perceive does not emerge because quantum superpositions are magically destroyed by consciousness or measurement. Instead, it emerges through a ruthless process of selection, amplification, and replication, driven by the relentless interaction of quantum systems with their surroundings. At its heart are quantum fluctuations, not as creators, but as the raw variation upon which selection acts. Imagine a single quantum particle, like an atom, existing in a superposition of two different positions at once. It is both here and there, a ghostly blend. This atom is not isolated. It is constantly bombarded by its environment, by photons of light, by air molecules, by the subtle gravitational pull of distant stars. Each of these environmental particles interacts with the atom, but in a very specific way. They do not measure the atom in the full quantum sense. They imprint a tiny piece of information about it. A passing photon might scatter off the atom differently depending on whether the atom is mostly here or mostly there. Crucially, the photon carries away that information into the wider world. Now, this happens not once, but countless times per second. A constant storm of environmental interactions probes the quantum system. Quantum Darwinism states that only certain quantum states, the ones that are most robust and leave the most consistent imprint on the environment, survive this onslaught. These are the pointer states. They are like the fittest variations in an ecosystem. A pointer state for position, for example, is one that does not rapidly spread out into a blurry cloud when photons bounce off it. It remains relatively localized. As trillions upon trillions of environmental particles interact with the system, they each make a copy of the information about these robust pointer states. The information about the atom being here is redundantly imprinted onto the photons, the air, the dust, everything around it. This redundancy is key. You, as an observer, do not need to perform a special, fragile quantum measurement. You simply intercept a tiny fraction of these countless copies that have been broadcast into the environment. You look at the scattered light or feel the air pressure, and you deduce the atom is here, because so many independent copies of that information exist. Any observer who checks will find the same answer. We all agree on reality because we are all sampling from the same widely distributed dataset created by environmental selection. The quantum fluctuations in the environment itself provide the constant, random probing that tests every possible state of a system. Most superpositions are fragile. They decohere, meaning their quantum phase information is scrambled and lost to the environment almost instantly. They are like delicate creatures that cannot survive exposure to the elements. But the pointer states are the hardy survivors. They withstand the environmental pressure, and in doing so, they get their information copied and propagated. In this view, the solidity of the chair you are sitting on is not an illusion, but a consensus reached by the universe. The chair's molecules exist in highly redundant pointer states, their positional information copied onto the surrounding electromagnetic field and air molecules so many times that any observation yields the same result. The quantum world is still there, buzzing with potential, but what we perceive is the outcome of a Darwinian struggle for existence in an informational ecosystem. The fluctuations that birth the cosmos have, through this process, given rise to a stable stage where only the fittest, most communicable states get to perform. Our classical reality is not the only possibility. It is simply the one that was best at getting its story told. The relentless selection of our classical reality points to a world of definite moments. But what if those moments are all that truly exist? Our final, 30th theory offers the most radical perspective of all. A vision where time itself is not a river, but a frozen landscape. Physicist Julian Barber proposes a shocking idea. Time is an illusion. There is no flowing past, present, and future. The universe is not a movie playing out frame by frame. It is a single, timeless photograph, or rather, an infinite gallery of every possible photograph, every possible configuration of matter and energy. He calls this gallery Platonia, a name evoking Plato's realm of perfect eternal forms. Within Platonia, every single static arrangement of every particle in the cosmos exists as a separate, complete reality. One configuration is our solar system, as it was 100 million years ago, with dinosaurs roaming the earth. Another is your room as it is right at this instant. Yet another is a future where the sun has become a red giant. These configurations are not connected by a timeline. They are just points in an unimaginably vast landscape of possibilities. This completely rewrites the story of quantum fluctuations. In Barber's timeless universe, those seething virtual particles and energy jitters are not events happening in time. They are the bridges between the points in Platonia. Our conscious experience of a flowing present, of one moment following another, is not us moving through time. It is our awareness jumping from one static configuration to a very similar, adjacent one in this landscape. Each jump is a quantum transition. Think of a movie reel again. We believe time is the projector light moving smoothly across the frames. Barber says there is no projector light, and there is no smooth movement. There is only the collection of frames, each complete and unchanging. Our consciousness is like a tiny spotlight that illuminates one frame, then instantly, quantumly, jumps to illuminate a nearly identical frame next to it, then another and another. The sensation of motion, of change, of time passing, is an artifact of this sequence of jumps between frozen snapshots. The reason the jumps feel smooth and continuous is that each now we experience is nearly identical to the one before, differing only by the tiniest quantum adjustments, an electron in a slightly different orbital, a photon having traveled a minuscule distance further. The entire history of the cosmos, from the Big Bang to the heat death, is not a story of evolution. It is a vast, pre-existing structure in Platonia. Our journey from birth to old age is not a process in time, but a predetermined path our consciousness takes through this landscape, hopping from one now to the next. In this view, the Big Bang was not a beginning in time. It is simply one particular configuration in Platonia, one point in the gallery. Our perceived expansion of the universe is just our consciousness traversing a sequence of configurations where galaxies are progressively farther apart. This resolves some of the deepest paradoxes of time in quantum gravity. It eliminates the problem of what happened before the Big Bang, because there is no before. It offers a new perspective on the arrow of time. The reason we remember the past and not the future is that the configurations we label as past are simply different points in Platonia that our consciousness has already visited along a particular thread of similarity. The future consists of points we have not yet jumped to. This is a profoundly beautiful and lonely vision. It means nothing ever truly changes, and nothing ever truly happens. All moments, your first breath, your greatest joy, your final thought exist eternally and equally, like jewels in a cosmic crown. You are not a story being written. You are a story that has already been written in full, and your conscious awareness is just a reader, turning the pages that were always there. The quantum hum we have followed through 30 theories is not the sound of creation. It is the silent mechanism of the page turner, clicking from one eternal now to the next, creating the magnificent, heartbreaking, and utterly convincing illusion that we are moving through a world of time, change, and consequence. From the cosmic egg of a universe born from nothing to the timeless gallery of every possible now, a single, ghostly thread weaves through them all. We have journeyed across 30 breathtaking theories, each one a different lens on the same fundamental truth. The quantum vacuum is not empty. It is the most creative, destructive, and mysterious substance in existence. It birthed galaxies from random whispers. It may hold the key to dark energy and dark matter, and it could one day erase everything in a bubble of true vacuum. It challenges our perception of reality, suggesting we live in a hologram, a simulation, or one branch of an infinite multiverse. It ties the fabric of space together with threads of entanglement, and may even whisper into the processes of life and consciousness. These are not just abstract puzzles for physicists in ivory towers. They are the frontier of human understanding, the very edge of the map where our questions about what is real, what is time, and why we exist are being forged. Every single one of these ideas, no matter how strange, springs from the same seething quantum foam. The solid world you touch, the vast cosmos you see, and the arrow of time you feel are all magnificent illusions built upon this foundational chaos. So we leave you with this question. Which of these 30 visions of reality reshaped your mind the most? Was it the holographic universe, the cosmic computer, or the timeless leap of a Boltzmann brain? Let the conversation continue below. Share the theory that haunts your imagination, and subscribe to journey with us into the next great mystery. The quantum whisper never stops, and neither does our quest to listen.